Swayam Prabha. Digital India. Educated India.
So let's get started. See, fundamental problem of networking in general, right, is how do we communicate across a distance? Long ago, we know that this was just pretty much messengers on foot and horse and stuff like that. A problem with this communication is this thing, right? Can be captured, delayed, this and that. In modern terms, we could say that being captured and delayed means that you have what amounts to mm, data corruption and false messages. So, in modern jargon, your messenger getting captured, this is what it means. Then a solution for that is that you could use fires or smoke signals from mountaintops and so on. Then you have weather as a problem, limited vocabulary as a problem. You can't convey the richness of a written message via smoke signals and fire. So there are channel failures, there are limitations on vocabulary and so on. And then people even tried some of these other cool things. So especially in Europe, after the telescope became popular, somebody invented this notion of semaphores, where you had a station on a mountain which would adjust these wooden rods at various angles, and then somebody is looking at them through a telescope, right? So because then that means that you can go across much larger distances, and significant parts of Europe were covered this way. So that's where many of these protocols originally evolved. They evolved in a world very different from ours, with no electricity and all that. And in those days, it was, I mean, not many things were science in the first place. And, telescope and all was the beginning of science. So there wasn't like that much thought on protocols as an idea, but some of the failure modes were known. So vocabulary, for example, has to do with the bandwidth of the channel. So some of these kinds of things people had begun to understand. And okay, so maybe this is better, so I can go one by one. The really hard lessons of protocol design were learned in the context of train accidents. So let's take a look at this example. Here is a little schematic. We have a tunnel with two tracks, one in each direction, and you have a side A and a side B, and there is a, so this really happened in this place called Clayton, right? And you had a signal man on this side, a signal man on that side. There were these semaphores, and this is after electricity, so there was a telegraph as well, but the telegraph had fairly limited vocabulary again, and this was the idea that they used to make sure that multiple trains aren't on one track and so on. And their protocol was like this: a train that sees green, so here green means a green flag which is set up by either uh, the signal man, or there is an automatic green light as well which is triggered. So a train sees a green flag or a green light, as the case may be, and it enters the tunnel, and as part of going into the tunnel it trips some mechanical device which then turns the light green, turns the light red, and only the signal man can now change the flag back to green. That was their idea of safety. So after the train enters, the idea was that, so in anyway this would prevent more than one train in one direction from going into the tunnel. But as a fail-safe, what they had was, after the train enters, the signalman A can send train in tunnel and he can raise a red flag. Then B will send tunnel is free after B sees the train coming out of the tunnel. And then also A can ask B using this needle telegraph, has train left the tunnel? Those are the three messages that are available to them. Because remember, when we say a needle telegraph, it's literally like a dial with a needle that has only three positions that you can tell more or less in a guaranteed way that this is where the needle is. But despite these precautions, the following things happen. One train T1 sees green, enters the tunnel, but something goes wrong in the mechanism, and the semaphore or signal, whatever it is, does not turn red. The signalman is alert. He notices this. He says, train in tunnel. He tells that to B and raises the red flag. But then a second train T2, which is coming behind T1, sees that green flag, and before the signalman can react, it enters the tunnel. As it enters, the driver sees that there actually was a red flag, right? Because the signalman just changed it as the driver was entering the tunnel. So he has noticed that. So far, so good. Nothing is wrong because the distance between the T1 and T2 is good enough, and things would have worked properly. Now what happens is a third train T3 comes in. It sees the red flag and it stops outside the tunnel. Still all good. Signalman then says, okay, when should I let T3 go? And he says, has train left the tunnel? Notice that this time something funky has happened. T1 and T2 are inside the tunnel, but the vocabulary of the trainman is limited. He can only ask, has train left the tunnel, right? There is no room in the vocabulary for T1 and T2 being in the tunnel at the same time. Now signalman B sees T1 leave and says tunnel is clear. But now we have a problem, right? Because what is the meaning of this? Is signalman A supposed to think about T1 or T2? Should he have, for example, decided that maybe I should wait? We don't know, right? Because these people are making these decisions every day. But there's a hole in the protocol. There's no room to speak about certain conditions. So T3 enters the tunnel and T2 has seen red. And T2, being a conscientious driver, decides to back up because maybe he sees that the signalman took some time to change the thing. And T3 enters the tunnel because signalman A says, yeah, okay, fine. The train has left the tunnel. Plus, he also thinks that, well, since one of the trains has left the tunnel, there's probably enough distance between T2 and T3 and things will be okay. And they might have been, except that T2 has existed on the border between green and red, which is exactly how traffic accidents happen today, right? Even conscientious people, while the light is changing, they may make this mistake, even in places with reasonable traffic discipline, because these transition conditions are very difficult for everybody to make sense of. And then, of course, there was a crash and killed 21 people and injured so many. So that's where, does your protocol have enough vocabulary? Does your protocol how will it fail? So what is the failure analysis here? And over time, people put together these things across many train accidents, and that's where the science of protocols was born. Okay. So then what are the problems to be solved in protocol design? First of all, you have three elements: sender, receiver, and channel. Now, channel may corrupt, reorder, or duplicate a message. How can this happen? Well, corruption can occur due to electrical activity, cosmic rays, various material failures. If retransmission is involved, so if you have some way to detect that maybe my message did not go across, you could retransmit, which can then create duplication because the earlier message is just delayed. There's a fundamental issue in all transmission. You cannot distinguish between delay versus failure, because if that's your only channel, how are you going to communicate failure of the channel itself? That is the fundamental issue. So then things like retransmission arise. And then if channel has store and forward elements, then you can also get reordering. There are other reasons for reordering where in our case, uh, elements of a single message can travel on different paths. And so you get another kind of reordering. So then these are the challenges. How do you recover from data corruption? How do you recover from duplication and reordering? How do sender and receiver distinguish start, end, intermediate message? Things like that, right? How does sender not overrun receiver? How do sender and receiver find each other? Because in our cases, the same channel is used to talk to multiple senders and receivers, right? So let's get started here. Now, I thought there was a nice way to control the presentation. Anyway, so let's take a look at the first problem you need to solve. That corruption can occur and how can you recover from data corruption. Now, this particular thing is a entire science in its own right, and I'll just touch briefly the kind of structure that is involved. So here is roughly the setting. You start with an electrical signal, which you chop off into bits, which you then gather into something like symbols and characters, which you then gather into a message, and which you then gather into even larger layers like packets and frames. Because ultimately, what is happening there is an electrical signal. And by the way, the electrical signal is shown like this for a reason, right? I mean, there's no such thing as a digital signal in real life. We what we do is we fake digital by deciding voltage levels. So now you can see, right? Some voltage increases somewhere, there is corruption. So things like that can happen. And then there are these higher order groups, like we said. And on top of this, now you can add ideas like files and pages and so forth. And then on top of that, what do you do with the files and web pages and whatnot, which is the actual world of applications that non-programmers especially, and when we are not acting as programmers, that's the world we actually live in. And so corresponding to these reality, levels of physics, you get what are called network layers. And if you haven't seen it already, you will hear soon about this very famous standard involving network layers. What's more important is to understand why the layering is done the way it is, because the idea is that you solve problems at each of these levels at that level, and then the layers above will take for granted what you have provided in the layers below. So example here is, there is these things called physical layers and data link layers, which correspond to this part, which is dealing with the conversion between the electrical signal and the digital layer. So this will typically be the physical layer, and this will typically be the data link layer. Next, once you have made all these messages, you need another layer which is above all this assembly, into a what is called a network layer, where you can identify machines and you can communicate to them. So the network layer effectively corresponds to what in our real life is a map, right? In when you're driving from destination A to destination B, you look up in the map, find out how to go, that kind of thing. So there's this network layer. And you get these variants. For example, you can have packet based layers, you can have virtual circuit layers. And I mean, these ideas largely came from our experience before, right? You can send stuff via post office or via courier or whatever, which is analogous to how the internet actually works, because you send these data packets. And then you have landline phones, so to speak, which were physical circuits of wires, which are then analogous to virtual circuits. And then if your network happens to be packet based, then every packet is of limited size. So what's going to happen is, if you're going to send a much larger message, you need a way to assemble those packets somehow. And then trade-offs between packets versus circuits. I mean, over the years, at various points, packets have been better than virtual circuits have been better, for whatever definition of better the implementer is using. And that's overall the idea. And in addition, there is a deep theory underneath all this, which deals with things like the fact that electrical signal transmission is error prone. you have all these strange problems from physics, and there are methods called error correcting codes and checksums, which are needed in every part of the computer, right? It's not just about networks. So there is something called ECC memory, because your memory can get corrupt. And literally there's a thing called bit flipping that happens when cosmic rays, which are these high powered particles traveling throughout space, will literally hit a memory and flip a bit from 0 to 1. So there are things like this as well. Plus, there are local problems in the chip itself and so on. And then file systems need to do something similar for disks and so on. Bottom line is, once the science has done the job of dealing with the error at higher levels, you can just say corrupt or not corrupt. So very simple binary decision. And then corruption means something has failed. I'm just going to retransmit. That's overall the picture there. And for this system, we kind of have to stop there, because that's, like I said, a whole other thing. And for the most part, most software engineers live in the world where that part is taken care of. And we are going to largely deal with how to transmit data correctly, assuming you can classify messages into good and bad. So that's the idea. So then now the problems to be solved become these things. Corruption is detectable. So how do you recover from duplication and reordering? And this is what actually network protocol is about, because it assumes the underlying world is nice and predictable. So if you have any questions, I'll wait for a minute and write them down, because I think the way this thing is structured, we have this little break and we can probably talk a little bit during that time. So try to write down things. I'll give you a couple minutes here to record any thoughts you might have. Right. So part one, fix the physical service so that you can pretend you can send messages, and then deal with these kinds of things. Now, remember what I said before, right? That retransmission can lead to duplication, but retransmission is necessary because you cannot distinguish between failure versus delay. How long are you going to wait until you are certain that whatever is happening is a failure? And then there are other things like, since we said the internet especially is packet based, so which means each packet can take a different physical route. So if your packets are part of a intended sequence, then reordering can happen. And then the second problem is, if there is a differential in speed between sender and receiver, then sender can overrun the receiver by sending too fast. So that problem is called flow control, and that's what much of protocol design tends to be about, followed by the last problem, which is these two, which is how do sender and receiver find each other and how do they establish a connection. I'm going to spend most of our time on these two parts, because this part, it's not that it's easy exactly, but it's easier to understand and gets talked about a lot, and we have some experience with it in real life, because we know that, for example, you need type in your domain name and you get a connection. So we have some idea how these problems are solved, but typically these are the things that people don't know about. So let's get started on that. So the first thing to understand in this is that there is an analogy between a protocol and a program, because a protocol is kind of a program. Let's go down that line by line. So we have, for protocols you have bytes, for programs you have characters. For a protocol you have a protocol format, and the format is fundamentally like this. It's the same thing that syntax is to a language. So how do you take the bytes together, arrange them in which order, etc., etc. So that's protocol format. Then you have, in a protocol, you have things called control messages, which we will see some examples of. and they correspond to reserved words in a program, because if your programming language reserves the word if, then when the compiler is working, the if tells you that now, okay, something is going to happen, and the compiler has to think about what's going to go on. Same thing with control messages. Data messages, on the other hand, are analogous to functions and variables, etc., that the user has chosen. So they have to follow the syntax, and they cannot use reserved words and so on. But other than that, they're free to do whatever they want. And then there is the environment in which the protocol works, which corresponds to operating systems in which a program executes. Then finally, you have service specification, which is what is the protocol supposed to do, and that corresponds to the specification of a program. So when thinking protocols, you should like keep this analogy in mind, which will help you think about a lot of these things. So what we are going to look at, right, we will implement as programs, but as far as the protocol designer is concerned, it's like the protocol designer is writing a program in this sense. What are the differences now? The differences are that, unlike most programs, protocols are inherently concurrent multi-party entities. So even today, most people, when they work on their apps and whatnot, will rarely write any concurrent programming, any concurrent programs. On the other hand, that is exactly what a protocol is. And inherently, it must deal with timing, race conditions, deadlocks, which makes protocols far harder to write than general purpose programs, because they are not sequential and they have to deal with failure. So let's take a look at a very simple protocol. These diagrams here, they are actually a programming language. It's called SDL, and you can get programs that can draw diagrams like this and convert them to C code or whatever code you want. So they're not just random flowcharts. They are designed for use with protocols. So here, simplest case, right? No flow control whatsoever, which we can start off with. There's a sender, there is a receiver. Sender just says next message, next message, next message, next message, and the arrow says the message gets sent. Now, this oval says the receiver normally just sits around and waits. Then it gets a message and it accepts it. All this assumes, of course, is that the receiver has what is the meaning of accept and how long it takes. Clearly, if you don't bother to limit the sender in any way, so typically, receiving a message is a harder problem, because you have to get it and you have to send it to the app and do something. But sending, the app has already given you the protocol what to do. It just has to blast these bytes across the network. Whereas in the case of a receiver, it's a harder problem. So sender just keeps sending, assumes receiver can keep up, right? Which means you aren't doing any flow control at all. And then there's a fundamental flaw here, which is the protocol should never make assumptions about relative speeds of communicating entities, because hidden in this is that there is a channel, right? Even if your receiver and sender are perfect, the channel can misbehave. There may be, it's essentially going from city A to city B. If the road is clogged, and then all of a sudden the clog gets removed, then you are going to get a large stream on the other side. And yeah, and since I'm going to give you these slides, etc., I put some of these things in here, SDL and so on. The next stage in the evolution of protocols is what are called X-on X-off protocols. So start and stop, basically. So here we have sender. So in this case, there are actually, this is the sender and this is the receiver. And within the sender and the receiver, there are independent threads of control. So here what is happening is, send a message, prepare a message, wait until you are told go by the other side, send the message. Then you have something that listens to what the receiver is telling you. So it says, well, am I supposed to suspend? If so, state is wait, and so then this process will be stuck. Am I supposed to resume? State is go, and then this guy can follow. So receiver explicitly tells the sender that please stop sending, and then afterwards says I'm done, resume sending. That's fundamentally the idea. And here you have, for example, on the receiver side, gets a message, increments it. If it's larger than its capacity, it will tell the system, it will tell the sender to suspend itself. And if it's false, it will keep on accepting. And then this is the actual receiving process, which says receive the message, and if it's accepted and you have capacity, then you can resume it. This one requires no speed negotiation or assumptions, but if suspend is lost or delayed, right? So receiver is asking to suspend, but the channel is wrong and the message is lost, then receiver will overflow. And if resume is lost, then the entire system grounds to a halt, because if resume is lost, the toggle here never flips and the state is wait, and that's that. There's no way for the receiver to wake up. So after that, you can say that okay, this is not good, and let's be more explicit about what's, the responsibility of resume should not be one way, because if it is one way, then you have a problem in that the system can stop. So then next thing is explicit ping pong, right? So which means you send a message, you receive an explicit acknowledgement that says I received your message. So it's not just that the message is lost. If it is lost, then somehow you can say that since I explicitly expect it, I can do other things besides just hang around waiting for this thing. So it solves the overflow problem, of course, kind of like what the Exon XOF does. But again, here, although you could get deadlock if the ACK is lost, you have room to do something else, which is to eventually add something like uh, a timeout here. Okay, I thought I had changed this diagram a little bit, but maybe it will come in a subsequent slide. So if you have a timeout, then you can say that okay, if I still haven't received it, I will send another acknowledgement, and I'll keep doing that until I get something. So we'll come to the timeout part later. Ping pong is simpler than Exon XOR, but it still has some of these problems. As it is, without timeouts, you still have this problem of getting blocked. And a second problem is, since the sender always waits until the receiver is done, whereas in the previous case, the sender can continue sending until this capacity thing is available, what's going to happen is that um, you will get a bunch of delays. So since one problem, there is some kind of explicit responsiveness between them, we can take an idea from the Exon XOF and build what is called a window, which is to say that the same kind of capacity thing where we decide prior to starting the whole thing that, okay, there is this much capacity available and the sender will keep track of capacity, but do it differently. It will actually get an acknowledgement here from the receiver. So receiver receives a message, accepts it, acknowledges it. The acknowledgement goes here. It says, okay, now since one of my messages has been sent, some capacity has been freed up, and I can go here. And while you are within the window, I can continue sending messages like that. So you start off by saying, I have a capacity of 10 messages. Start sending. Receiver says, okay, I received one. So if you have already sent, say, 3 or whatever, your capacity is now bumped back up to 8, because you could have sent 7. You just received that the receiver received at least one. So that means now you can send 8. That's the basic idea. And so in a separate protocol, the receiver will tell the sender where the W comes from and acknowledge each message. Now, if they are lost, you will still need to do retransmission, but at least you have a fairly responsive setup compared to X on X-on. And this is the heart of it. This is where interesting things start getting happen. So you have losses, you have timeouts, and you have retransmission. So first, this is ping pong with timeouts. So which means I'm waiting to receive, but if I don't get anything, I'll time out and I'll send the same message over and over again. And you could imagine that that's the same thing you should do on the receiver, because maybe either of them should wake the other guy up. But having timeout on both sides causes interesting problems. So you could uh, uh, use that. The important lesson is that only one side must use timeout for interesting reason. So suppose sender has sent a message, receiver has acknowledged, but both were delayed more than the timeout. Now the question is, should the sender retransmit? But if it retransmits and gets an acknowledgement, how is it supposed to know which one is the acknowledgement for? Is it for the original message or is it for the retransmitted message? And if it is for the original message, then should I wait until my retransmission is acknowledged? Right? It's somewhat puzzling. So uh, you could tell this on if you start numbering the messages and numbering the acknowledgement, but otherwise there is no simple way to understand. And in the case of protocols, these things have a cost. So numbering is not free. This is not an ordinary program. It's often in a tightly constrained space, working at the bottommost layer, and often across very tricky devices, and every extra byte you decide to send takes away capacity from the channel. Now, in an age where we watch videos over cell phones, this doesn't seem like much, but it adds up to a surprising degree. So the question, if you, for example, think of say numbering a message, how many messages should we number? You can't just keep counting. If there is like a video channel, billions of packets are going to get exchanged. Should I reserve capacity to say how many billions exactly? Because if the conference or whatever is going on for 3 hours, 6 hours, whatever we are doing, for instance, just how much space is should be reserved to number all these messages? And then suppose you say, okay, I'm going to limit the number I'm going to send. Now, if you recycle the numbers, then a new question arises again, which is this an acknowledgement for an older message? So, numbering and all can help, but variations of this problem keep on coming. So, the basic rule is timeout should be on one side. Usually, it is on the sender side because the sender has control over what is going on. But technically speaking, you could build a receiver timeout based system. So this is the part which makes protocol design difficult. And one very clever solution to all these things was given in what is called the alternating bit protocol. Those of you who have studied networking will recall this. We'll take a quick look at it. Let's see what time it is. And 10:38. Okay, so I have 20 more minutes. Right. So this thing is the alternating bit protocol, and it does something very simple to solve this sequence numbering problem. So you want sequence numbering because of timeout, you want retransmission, but you want to match the message sent with its acknowledgement. And so the simplest case is was created by the alternating bit protocol. The idea here is like this: the receiver has the capacity for just one message. And so what you do is you keep sending. So these underlines are sends and the others are receives. So let's say you are here in this state, or you could be here in this state. And the idea is you keep sending A0. So you send A0, but from the receiver, you get B1, in which case you should keep sending A0. When you get B0, you go to this state. Symmetrically, now start sending A1. So these A1, A0, these are just labels attached to the messages, right? The message itself is whatever your data content is. For the protocol designer, that doesn't matter. They are just interested in exchanging the data somehow. This is where you step away from, we talked about control messages versus data messages. So when you are doing protocol design, you stop thinking about the content. You just say, what is my control level? So you are actually designing the keywords of a new programming language when you design a new protocol, to use the analogy we just looked at. So, and then on the other side, the system is exactly symmetric, right? There's no distinction between sender and receiver, except who sends things labeled A and who says things labeled B. And the same idea is on the other side. Keep sending B0 until you get A1. So B0, if you still get A0, keep doing this. And if you look at the progression from no flow control to X on X off to ping pong with windows to something like the alternating bit protocol, you'll realize that the alternating bit protocol has, because of its symmetry and because of its design, it has collapsed the amount of variation that exists in the implementation of the protocol. So it guarantees that since the pairs of zeros and ones alternate, you cannot confuse one for the other. And once you see this, it seems very, very obvious, but it was a kind of a breakthrough. And it still is a sort of a paradigmatic example of designing a simple and correct protocol. So I'll wait here for a bit, because we went reasonably quickly through the evolution of protocols, and give you some time to think. And towards the end, you can ask me to revisit these slides. So now that you have the basic idea clear, you can start doing things like this. So this is the alternating bit protocol with timeouts. And here, as we discussed before, only one side should time out. So the sender can keep going like this, as long as you switch the R and S, what is received and what is sent, and then flip it. So since it's only 1 and 0, the subtraction here says that you are flipping the bit, and the same thing continues on the receiving side. And then, of course, this is not a problem because every alternate message matches its acknowledgement. So that's the overall sort of skeleton idea of the hardest problem in protocol design, which is flow control. And now, I mean, we have solved it. It's not like an open problem anymore, except that the problem will recur at a higher level. So even if you have your transmission correct, essentially the same thing happens in a web browser application. Because let's say you are submitting a form written in a web app, you are placing the order, and you place the order, but the other side doesn't quite receive it. So what are you supposed to do? And how long are you supposed to wait? Are you supposed to retransmit? So that's why, the submit button, you used to see this thing. I don't remember anymore. I think with the uh, use of mobile phones, some of this stuff has gone away. But the apps will gray out like the submit button and will not allow you to submit something again and again. And internally, what the app has to do is effectively maintain some kind of a sequence number, that this order has been placed. It has a sequence number. And if you keep placing multiple orders, you need to distinguish them somehow. So this concept of uh, messaging and acknowledgement, and the idea that you have to do this match, and also the idea that you have to deal with timeouts, it recurs even at the human level of the application. Because if your order fails, you are still going to wonder, should I resubmit, right? And another example where you see this sometimes in these when you're doing these e-commerce orders, you are supposed to get a OTP. Now, the OTP systems, they will internally have a timeout, right, which says that wait for 30 seconds before requesting another OTP. Because you have the same problem. You don't know whether the OTP that you were receiving was actually lost or just delayed. And by sending you a new OTP, so I have sometimes done this, right? You get impatient and you get a bunch of OTPs and you don't know which one was the OTP for. Is this the delayed thing from my first attempt, or is it a new OTP? And if you happen to, put in the early OTP or something after requesting a second one, then you'll say incorrect OTP, blah, blah, blah. So it is not just a low level protocol design issue. Any kind of interaction, whether it is people, whether it is programs, will have these fundamental issues of flow control built in. We experience this in daily life, even in, I sent you this email, why didn't you reply, right? Did you not see it, or are you choosing to ignore it, or what just happened? So the fundamental notions recur again and again in various different contexts. Now, besides this, how do real protocols differ from our simple examples? Fundamentally, larger window sizes. Then you can do clever things like you can acknowledge an entire block of messages rather than sending acknowledgement for every message. You can do other things like, let's say I haven't received something, then the receiver can send a message which is sometimes called negative acknowledgement, which says, hey, I was expecting something, but I didn't receive anything. Again, in daily life, you didn't get a reply from somebody for an email. You do send a negative acknowledgement which said, hey, aren't you supposed to reply? And then, you get these polite little things, reminder, blah, blah. It's like you don't want to piss off the other fellow, but at the same time, you are expecting something to happen which hasn't happened. And then there are other complications. For example, we talked about window sizes. So window size needs to be determined dynamically, and there are various dynamic algorithms that take into account the channel capacity and various other complicated things when a real protocol is getting built. So that's flow design. So wait here for a minute. Need to think about it. And by the way, use the analogies that I gave you. The OTP, email communication. If you haven't studied this yet, it's better to study it with real life things you have experience with than abstract protocols which talk about zeros and ones and whatnot, because that's not how anybody thinks actually. It's just that after you are done thinking about the intuitive situation, you capture it in a finite state machine or something like that, which is easier to think about mathematically than intuitive situations. So that's other reason why flow control is important, because most of us are going to be building distributed apps which involve communication, and we will have to solve these problems. So the lessons from that train crash and all that will recur in our lives under less catastrophic circumstances, hopefully. Right. So real protocol features, and then the remaining problems, those are relatively easy. We considered these, and we considered duplication and reordering. And then the next two are how do you distinguish start, end, and intermediate messages, and how do sender and receiver find each other. So we'll talk a little bit more about these problems in the second thing, but I'll just visit them somewhat briefly. Routing, I hope all of you have some idea of what is going on when we use these websites, that every machine has essentially a human readable address, which is the domain name service. Every machine has a machine readable address, which is the IP address. And then given the destination IP, you find a route via intermediaries, which is done using actually algorithms which are very similar to those used by your Olas of the world, or Google Map or what have you, because it's fundamentally the same problem. These things like Dijkstra's shortest path algorithm and all, if you have seen that, is variations of that are used even on the internet. And then what are these intermediaries? Well, intermediaries are owned by these service providers. And the entire dynamic distributed graph is maintained by things like routers, gateways, and whatnot. All of us have a router at home. So that's a participant in this business. Okay, now how do you establish connections? This part is, if you go on the net and try to see the TCP state machine, it's hideously complicated, but I will try to, because it takes care of a lot of crazy situations. And it also is a symmetric state machine, kind of like our sender and receiver in the alternating bit protocol. So I'll try to make it look more like a programming language. Although I didn't find a nice enough diagram that I really liked. But I would have liked to show. You can see this diagrammatically a bit better. But let's look at it as a linguistically. So server is listening, client gets open from the app, and we are going to use question mark to say receive and exclamation mark to say send. So client is initially these brackets I have used for states. So client is in closed state. App open question mark means it gets a open from the app. Then it sends a packet to the server, which is called a syn packet for synchronize. It's a strange name. I never much liked syn, but well, stuck with it. Then it says I'm going to go to a new state, which I will call syn sent. And then I'll wait for an acknowledgement from the server, which is called a synac. And when I get synac, I'm going to acknowledge back, which is called act. So app open syn. So app open comes in, syn goes out. Synac comes in, act goes out. So that's called a three-way handshake. And now you move to the established state. On the server side, you are in listen state and you get a syn. Then you send a synac, kind of the exact mirror image of these two here. Then you get into syn received and you get an act back. You're waiting for an act. And when you get an act, you go to the established state. So this act matches that act, and the syn act here that is sent matches this syn act. So you could think of it as act 1 and act 2, but these are the traditional names. When this happens on the server side, it spawns off a new what is called a transmission control block to represent a ongoing circuit, and now data transmission and flow control goes on. Then let's say the server decides to close or get some request from the server app to close connection. Then it says, okay, we are both in the established state, which we got into here. So the server says, okay, send fin, because server is deciding to close. Client says, in established state, I'm going to wait for fin. And when I get fin, I'll send a finac one. Then I'll go into this state called close wait. So this is the client. Server meanwhile goes into fin wait one, waits for the finac one to come in. So you match the exclamation mark on one side with the question mark on the other side. When I get a FINAC, I go into a second wait state, a FIN wait, and then the second thing the client does is, okay, I acknowledged your FIN message. Now I'm telling you that, okay, I'm doing FIN myself. I suppose we could have labeled this FIN S and FIN C or something, so that I'll do that in the slide before you get it, so that you can match the fins better. So this one waits for S fin, and this guy sends S fin, something like that. And the client sends a C fin, and the server waits for a C fin. Right. And so then the client sends a client finished, and waits for a FINAC2 from the server. Server says, is client finished? Yes, I'll send a FINAC2, and then hang around. And I mean, depending on the setup and where you are, either the time, it goes into a state called time wait, which then expires, and finally you get to closed. Now note that this is one funky thing, right? On the server, the connection is closed, but the server itself is still in listen state, because I mean, just because you closed one connection doesn't mean you aren't serving other people. So there's a bit of a asymmetry here. And if you look at the maybe when I was looking at this, I realized that maybe we should write some small JavaScript program to show animations between the state machines on the two sides, but I'll do that someday. Right. So that's the setup of the connection, and here is a quick summary. So problems: get data across uncorrupted, manage flow of data. Remember those OTP and email problems in our daily life. That will help you get a sense of what is needed. Then distinguish connection establishment, etc., from normal traffic. Manage server discovery and routing, I should say. So more study, of course, I mean, you will have your textbooks, whatever your schools are doing. Plus, we'll take a quick look at these tools later on, NetStat, SOCAT. You really need to get good with tools, because we have, the internet is a fact of life, and in, in addition to studying abstract network theory, you also need these things. And much of what I showed you comes from this book. I've heard that it went out of print or something. I haven't looked in a while. It's like a real shame if it's true. But I think there's an online copy available. Gerard has put it on his thing. So I actually worked very briefly with him long ago. And that's probably why I know about this book. So that's our trip through network protocol fundamentals. Right. So I hope you have had some time to write things down, and maybe you have some questions, or maybe you have studied this already. I don't know. I'll open up the meeting for questions.
Hi, can we ask questions via
Yeah, go for
voice? Great, thank you. So a couple of questions. First one was that, I mean, these protocols are designed at the protocol level, right? I was wondering about the underlying system that implements these protocols, for example, these routers, and also in modern IoT based, I mean, we call this IoT, but what I like to think of this as this hyper-connected environment. The number of requests, the number of packets, it is exponential, right? Billions and billions of packets. Whereas the system that is powering these communications, do these systems actually have the capacity to process billions of packets? Because clock speeds are limited, right? Clock speed is saturated at 3 gigahertz, and I don't see it going beyond that. So uh, there is how do you balance those kind of throughputs, and which are obviously expected to scale much more?
Well, Okay, so first of all, don't use words like exponential, right? That's like a when you are a computer science student in a computer science context, exponential has a specific meaning. So don't use, I mean, I know that in the general world, exponential has nowadays changed to mean something like very large, right? But exponential in our context has a specific meaning. So capacity problems have existed in relation to our ability to communicate pretty much from the beginning of the world. And I think they will exist for a very, very, very long time to come. And a simple answer to your question is actually that two kinds of things happen. One is that, like you said, there are these clock speed evolutions which may run into some limit. These gigahertz limits and all those are true for very complicated things like CPUs. But if you really put your mind to it, you could do specialized chips that are simpler than a general purpose CPU. And there are reasons to do it and not do it and so forth. But you could. So you could eke out some more progress from the clocks. But that's not the point, right? The simplest way is to simply multiply more of what you have. So most of the breakthroughs in Wi-Fi, for instance, are a combination of just how many uh, antennas you can put in, because each antenna can work separately, versus you use these things like Fourier transforms and whatnot and wavelet transforms to use the same airspace, so to speak, electromagnetic spectrum space available, and use it much more efficiently. So there's probably some room available there still. And if not, you just go for parallelism. You just have more devices. That's basically it. So a search company like, so I used to, I was a search architect once upon a time. And you may or may not know this, but a search company basically has a copy of the entire web. That's how it knows how to search. And you can actually, I mean, somebody like Google probably now has hundreds of millions, if not more, machines. So you just multiply the machines, multiply the channels. That's how you get across.
Yeah, so horizontal scaling, obviously. I
If,
mean, yeah,
if
horizontal,
yeah,
that is horizontal scaling, right?
yeah,
Yeah, I was focusing on the vertical part, but yeah, that makes sense. Thank you
yeah,
for the answer.
sure.
The second question that I have is that I see, I mean, these protocols are obviously great and they power today's infrastructure, but if I look a decade from now, there's this huge thrust on cybersecurity and especially Byzantine faults in modern networks, right? So, is there any work which tackles specifically these kind of Byzantine faults or a security-based perspective? I mean, one question can be that a security-based perspective on this protocol design, or the second question can be that where do you see protocol design a decade from now?
Um, the part of protocol design we looked at regards security as a separate concern, and you usually handle security with some what amounts to encryption of one kind or another, fundamentally. So that way the problem lies not in the protocol design but in the data traffic design. That's how you do the separation. And uh, I mean, faults of different kinds have been studied and will keep on getting studied. As far as where protocol design goes, it's generally the security people will not talk to the, or will not need to talk to the performance people, right? um, because they have separated, they have given the security problem to the put it, do whatever you want, we'll just get your bytes across. And the performance people are just treating this entire network as a single system. And I mean, I guess a good answer is What would be a good answer that would make sense to you? So there is a field of study called control systems, and there is something called queuing theory, which basically deal with how to get a lot of things how how to get a lot of things done in very large systems. Sorry for being vague, but it's okay. Do I have a better answer than that? Okay, fine. So here is a better answer. TCP has something called slow start, and slow start is an idea that comes from electrical engineering actually. So if you have a say is there a better analogy than that? Okay. Think of it. So there is a device called a flywheel. Okay, a flywheel is a very large wheel that costs a lot of effort to get turning, and then costs a lot of effort to stop turning, because it by design it is heavy, and its job is to maintain inertia. It's hard to get started and it's hard to get stopped. So what happens is, a flywheel, you get it started very very slowly, and eventually it reaches its top speed. And curiously enough, that is the thing you need to do in a network. So for example, if a new device comes online, it doesn't get all the bandwidth it possibly could. It is forced to go into something called slow start, which basically says that let's exchange a few packets to get a sense of how loaded the network is. Because you can think of the entire network as a kind of a loaded flywheel. And if there is room, then you can spin the flywheel and put more inside it, but the growth will happen very, very slowly. So that's an example of traffic smoothing. So it is like there is this different universe of large scale system design that comes into play. I hope the flywheel analogy worked. I don't know, I haven't. I mean, things like slow start and all are so natural to somebody who studied electronics and electrical engineering that it's tricky to come up with analogies that make sense to other people, I guess. I'll think about it. If I can think of something, I'll say it in the next session.